On June 2nd, 2026, Microsoft stood on stage and claimed it had just made its quantum computer chip 1,000 times more reliable than it was 1 year earlier. That's not a small upgrade. That's the kind of jump that normally takes an entire industry a decade to pull off. But here's the part almost nobody is talking about. Within hours of that announcement, some of the most respected physicists in the quantum computing field came out and said the exact same thing they said about Microsoft's last chip. They don't believe the core claim actually holds up. Stick with me to the end, because this story has two completely different versions depending on who you ask. And by the time this video is over, you'll understand exactly why serious scientists are split right down the middle on one of the biggest quantum computing announcements of the year. If you want more stories like this, one that gives you both sides instead of just the flashy headline, hit subscribe now, because this channel doesn't do hype without the receipts. Instead of relying on superconducting circuits or trapped ions, Microsoft's approach tries to create what's called a topological qubit, based on a strange theoretical particle called a Majorana quasi-particle. Here's the basic idea. When you cool certain materials down to extremely low temperatures and arrange them in specific superconducting wires, electrons inside that material can start behaving collectively, acting almost like a single new kind of particle sitting at each end of the wire. Microsoft's design places two of these wires side by side, connected in a shape like the letter H, which together forms a single qubit built from 4 of these Majorana quasi-particles. The theoretical advantage is enormous if it actually works, because information stored this way is described as non-local, meaning it's spread out between 2 separate points instead of sitting in one fragile spot, which in theory makes it naturally resistant to the small disturbances that normally cause errors in quantum computers. Imagine trying to erase a message that's written using invisible ink, split across 2 different pages instead of 1. You'd have to disturb both pages in exactly the right way at exactly the same time to actually destroy it. That's roughly the kind of protection Microsoft is chasing. The particle at the center of all of this has a genuinely strange scientific backstory worth knowing, because it explains why physicists take this field seriously even while they argue fiercely about whether Microsoft has actually built what it claims. The Majorana particle was first proposed in theory back in 1937 by an Italian physicist named Ettore Majorana, who described a particle that would be its own antiparticle, an idea that sounds almost like science fiction but is grounded in legitimate, decades-old quantum theory. Majorana himself famously disappeared under mysterious circumstances shortly after publishing this theory, and his fate has never been fully explained, adding an odd historical footnote to a field that's already full of strange physics. Real, standalone Majorana particles have never been directly observed floating freely in nature. What Microsoft and other research teams around the world are chasing instead are Majorana quasi-particles, collective behaviors that emerge inside specially engineered materials, effectively simulating the properties Majorana originally predicted, without requiring an actual fundamental particle to exist on its own. The broader technique Microsoft is banking on is often explained using an analogy to braiding, similar to how weaving several individually weak fibers together produces a much stronger rope than any single fiber could manage alone. By manipulating multiple Majorana quasi-particles together on a single device and effectively braiding their quantum states around each other, Microsoft's theory holds that the resulting qubit becomes dramatically more resistant to the kind of small, random disturbances that constantly plague other quantum computing approaches. If this braiding-based topological method genuinely works at scale, Microsoft has claimed it could eventually allow millions of qubits to fit onto a single chip, a scale most competing hardware approaches are physically nowhere close to reaching, since their individual qubits typically take up far more space and generate far more surrounding interference. Now here's what specifically changed between Majorana 1 and Majorana 2, and this is where the numbers start to sound genuinely dramatic. Microsoft's team swapped out the superconducting material inside the chip, moving away from aluminum, which is what Majorana 1 used, and switching to lead instead. That might sound like an unusual choice, and honestly, even Microsoft's own team seemed to admit as much. Chetan Nayak, a Microsoft technical fellow who leads much of this research, told reporters during the announcement that people generally try to avoid putting lead into anything, and admitted the idea sounds a little crazy on its face, but lead has a specific property that matters enormously here. It does a much better job shielding delicate qubits from outside interference, things like background radiation and cosmic rays constantly passing through the atmosphere, both of which can quietly knock a fragile quantum state out of alignment without any warning. According to Microsoft, that single material change, combined with a redesigned materials stack underneath it, produced a genuinely massive jump in stability. The company says Majorana 2's qubits maintain their quantum state, technically called coherence, 1,000 times longer than the first generation chip managed. In real numbers, Microsoft is reporting a mean qubit lifetime of about 20 seconds, with some individual qubits holding their state for as long as a full minute. For context, most competing quantum computing approaches today measure coherence time in microseconds, millionths of a second, not seconds or minutes. Microsoft compared the jump to inventing a phone battery that used to die within a single day, suddenly lasting almost 3 years on one charge instead. Whether or not you end up believing every part of Microsoft's claim by the end of this video, that comparison alone tells you how big a leap the company says it just made. The chip itself is tiny too, roughly 1/100th of a millimeter, and Microsoft says its operations run in about 1 microsecond. Extremely fast by quantum computing standards. Right now, the working system is built around what Microsoft calls a 4-qubit array, a small foundational block designed specifically so it can be expanded gradually over time rather than needing to be redesigned from scratch at every larger scale. That detail matters a lot for the bigger picture Microsoft is selling, because the whole pitch behind the topological approach has always been about long-term scalability. Back when Majorana 1 was first unveiled, Microsoft described its underlying architecture as a topological core, specifically engineered with an eventual goal of supporting systems with as many as 1 million qubits on a single chip, a number most competing quantum hardware approaches are nowhere close to reaching, largely because their qubits take up far more physical space and generate far more heat and interference at that kind of scale. There's also a genuinely interesting twist buried inside how Microsoft says it actually built this chip. And it connects directly to something else the company has been pushing hard all year: artificial intelligence. Microsoft says Majorana 2 was developed with direct help from something called Microsoft Discovery, the company's agentic AI research platform, which became generally available to the public the same week as the chip announcement. According to Zulfi Alam, corporate vice president for quantum at Microsoft, building devices like this requires designing critical components atom by atom, getting the exact right amount of specific impurity materials added into the crystal structure without throwing off the whole design is an extremely delicate balancing act. In the old process, Alam explained, that meant a huge amount of trial and error in the physical lab. With AI agents running simulations first, the team could identify the most likely successful target before ever stepping into the lab, then largely only needed to run the physical experiment once to confirm it. Nyack backed this up too, describing the use of agentic AI to automate the endless stream of measurements the team needed to take during the chip's design as, in his words, a genuine game changer. The AI agents reportedly combed through more than 2 decades of existing quantum research data, and, in the process, actually caught a previously unnoticed, miscalibrated temperature sensor buried somewhere in the setup, an error that had apparently been quietly affecting results without anyone catching it. Microsoft is framing all of this as proof that AI and quantum research are starting to accelerate each other, with better AI helping build better quantum hardware, which will eventually help run even more powerful AI, a feedback loop the company clearly wants investors and the public to start paying close attention to. Based on everything you've heard so far, Microsoft's confidence makes a lot of sense. The company backed that confidence up with a bold, specific claim about its own timeline. Microsoft says this progress has allowed it to accelerate its roadmap significantly, moving its target for delivering a scalable, commercially useful quantum computer from 2033 up to 2029, cutting 4 years directly off its own previous public estimate. The company argues a machine like that could eventually help tackle major real-world problems in areas like global health, food supply, clean energy, and sustainability, categories of problems that involve extremely complex simulations classical computers currently struggle to handle efficiently. Jason Zander, the Microsoft executive vice president leading the company's quantum team, called this a genuinely exciting era for the field during the press briefing. If everything Microsoft claims here turns out to be accurate and fully reproducible, this would represent one of the most significant hardware breakthroughs in the entire history of quantum computing. It's worth spending a moment on why those specific application areas, global health, food supply, clean energy, keep coming up whenever quantum computing companies talk about their long-term goals. Because it's not just marketing language. There's a real technical reason behind it. Many of the hardest problems in those fields ultimately come down to simulating how molecules and materials behave at the quantum level. Things like predicting how a new drug compound will interact with a specific protein, figuring out how to design a more efficient fertilizer that doesn't waste as much nitrogen, or finding new battery materials that can store more energy without degrading as quickly. Classical computers struggle badly with these particular simulations because the number of possible quantum states involved grows exponentially larger with every additional atom you add to the model, quickly overwhelming even the most powerful supercomputers on Earth once you're modeling anything more complex than a fairly small molecule. A genuinely stable, large-scale quantum computer built on qubits that actually behave the way quantum theory predicts could in principle simulate those same molecular interactions far more naturally, since it would be using quantum mechanics to model quantum mechanics instead of forcing a classical machine to painstakingly approximate it. That's the real prize. every major quantum hardware company, Microsoft included, is ultimately chasing not just faster arithmetic, but a fundamentally different kind of computing that's naturally suited to a category of problems. Classical machines may simply never be able to handle efficiently, no matter how much raw processing power gets thrown at them. And that word if is exactly where this story takes a sharp turn, because the moment Microsoft's announcement went public, a meaningful number of independent physicists who don't work for the company pushed back hard, and their objections aren't small technical nitpicks. They go straight at the heart of Microsoft's central claim. To understand the pushback, you need to understand one basic fact first. While this specific announcement is based on a new preprint research paper, meaning it has not yet gone through formal peer review by other scientists, the standard process, where independent experts scrutinize a study's methods and results before it gets published in a recognized scientific journal. That doesn't automatically mean the claims are wrong, but it does mean the wider scientific community hasn't yet had the chance to formally check Microsoft's work the way research normally gets checked before being treated as settled science. Here's the specific technical problem several physicists raised, and it's worth explaining clearly because it's the exact same criticism that dogged Microsoft's first Majorana chip back in 2025, proving that a topological qubit genuinely exists and works the way Microsoft describes requires two different kinds of measurements, referred to in the field as X measurements and Z measurements. Microsoft's new paper on Majorana 2 only presents Z measurements. Henry Legg, a physicist at the University of St. Andrews, who has been one of the most vocal skeptics of Microsoft's Majorana research going back to the original announcement, said flatly that nothing in the newly presented data actually proves the existence of a topological qubit or genuine Majorana particles inside these devices. He's not alone in that assessment either. Sergei Frolov, a quantum researcher at the University of Pittsburgh, who has closely tracked and publicly questioned this entire research program for years, was even blunter, saying that whenever Microsoft's quantum work comes up in conversation these days, physicists and specialists in the field tend to just chuckle or raise their eyebrows. Frolov specifically pointed out that this new preprint isn't built on what he considers a solid, established research foundation to begin with, referencing years of prior disputes, corrections, and even outright retractions tied to earlier claims made about Majorana particles, both from Microsoft's team and other labs working in the same general area of physics. To be fair to Microsoft, and to give you the complete picture instead of just the criticism, not every outside scientist dismissed the new results. Kartik Agarwal, a physicist at Argonne National Laboratory who is not affiliated with Microsoft, reviewed the new measurement method the team used to probe what are called the non-local properties of these Majorana particles, and he described it as genuinely supporting the case that these really are Majoranas, calling the progress fantastic. So this isn't simply a case of the entire outside scientific community dismissing Microsoft's work outright. It's a genuine, active, ongoing scientific disagreement with credible researchers, landing on meaningfully different conclusions after reviewing the exact same published data. That's actually a fairly normal and healthy part of how difficult cutting-edge physics research plays out publicly, especially at a frontier this contested. But it stands in sharp contrast to how confidently Microsoft's own public marketing and press briefing framed these results to journalists and the general public. Microsoft's leadership hasn't stayed quiet in the face of this skepticism either, and their response is worth hearing directly, because it captures exactly how differently the company sees its own position in this argument compared to its critics. During the press briefing, Jason Zander offered a comparison that's been repeated widely since the announcement, saying that Bell Labs, the famous research lab that invented the transistor decades ago, never had to formally prove that the electron itself existed before building a working revolutionary device around it. Zander argued that in Microsoft's case, the situation is actually harder, because the company did have to prove that Majorana particles and the underlying theory behind them are genuinely real before it could build anything useful on top of that foundation. It's a clever historical analogy, and it does capture something true about how applied physics sometimes moves ahead of complete theoretical certainty. But critics like Legg and Frolov would likely respond that the entire disagreement here isn't really about whether Majorana particles could theoretically exist somewhere in nature. It's specifically about whether Microsoft's current chip design has actually conclusively demonstrated them working the way the company claims. And on that much narrower, much more specific question, the skeptics remain genuinely unconvinced by what's been published so far. It's worth stepping back here and putting this entire Majorana saga into a bit of historical context, because this isn't actually the first time Microsoft has faced this exact kind of criticism over this exact research program. Back in 2021, a separate Microsoft-linked paper claiming to detect Majorana particles had to be formally retracted from a major scientific journal after other researchers found serious problems with how the original data had been selectively presented. That earlier controversy actually traces back even further to research published around 2018, when a Microsoft-affiliated team first claimed strong evidence of Majorana particles in a device, a claim that generated enormous excitement at the time before independent researchers began raising questions about the way the underlying data had been filtered and presented, eventually leading to the formal retraction 3 years later. That history is precisely why so many physicists reacted to this new Majorana 2 announcement with immediate, practiced skepticism rather than simple excitement. They've been burned by bold claims from this exact research direction before, and they're understandably far more cautious the second and third time around. Microsoft, for its part, has consistently maintained that its more recent work, including the original Majorana 1 announcement from 2025, addressed the specific problems that caused that earlier 2021 retraction, and that its measurement and verification methods have meaningfully improved since then. Independent physicists remain split on whether that improvement has actually gone far enough to settle the underlying question. This pattern of bold announcement followed by outside scrutiny isn't unique to Microsoft either. It reflects something genuinely difficult about this entire corner of physics. Detecting and confirming exotic quasi-particles like these requires an extraordinary level of precision, involves interpreting extremely subtle signals buried in noisy experimental data, and often comes down to judgment calls about which measurements count as sufficient proof and which don't. Several other research groups around the world, working at universities and national labs unconnected to Microsoft, have pursued similar topological qubit designs over the past decade, using slightly different materials and configurations, and more than one of those independent efforts has also produced results that were later challenged or walked back after closer review. None of that means the underlying theory is wrong. Physicists broadly agree. Majorana quasi-particles should theoretically be achievable under the right conditions, but it does help explain why the entire subfield has developed a culture of heightened caution whenever a new headline claim shows up, regardless of which lab or company is making it. So, what does all of this actually mean if you're trying to figure out how seriously to take Microsoft's Majorana 2 announcement? The honest answer sits somewhere between the two extremes you'll find online. This is not simply a fabricated claim with zero scientific merit. Microsoft's team includes genuinely respected physicists. The underlying theoretical framework around topological qubits is taken seriously across the broader physics community, and even skeptical researchers like Agarwal see real value in specific parts of the newly published measurements. At the same time, this is also clearly not a fully settled, universally accepted scientific breakthrough the way Microsoft's press materials and public messaging tend to present it. The gap between a corporate press release confidently announcing a 1,000-fold improvement and a peer-reviewed, independently reproduced scientific result that the entire specialist community agrees on is a real and meaningful gap. And right now, Majorana 2 sits somewhere in the middle of that gap, not yet fully across the finish line either way. There's a useful way to think about why this particular gap matters so much here, more than it might in other areas of technology reporting. In most industries, a company can ship a slightly exaggerated product claim, and the market simply sorts it out later. Customers try the product, reviews come in, and reality eventually catches up to the marketing. Quantum computing hardware doesn't really work that way yet, because there's no working commercial product on the market for ordinary customers, or even most enterprise buyers, to test and independently verify for themselves. The only people currently in a position to check Microsoft's claims are a fairly small, specialized group of physicists capable of reading and critiquing the underlying preprint data, which means the normal checks and balances that usually keep corporate claims honest, real-world usage, competitor benchmarking, independent product reviews, simply don't fully exist yet in this specific corner of the tech industry. That's exactly why voices like Legg and Froloff end up carrying so much weight in this story. They're functioning as one of the only real accountability mechanisms currently available while this entire field remains this early and this specialized. It's worth putting Microsoft's approach next to what its biggest rival in this space is doing, because the contrast tells you something important about just how many genuinely different paths companies are betting on right now to reach the exact same destination. IBM, which builds its quantum computers using superconducting circuits rather than Microsoft's topological approach, has already deployed more than 90 separate quantum systems globally as of June 2026, working with an ecosystem of over 325 Fortune 500 companies. IBM has committed more than $10 billion in additional investment over the next 5 years, with a public roadmap targeting a prototype called Quantum Starling by 2028, aiming for 200 logical qubits built from roughly 10,000 physical qubits, followed by a full-scale fault-tolerant commercial system by 2033. That's notably a slower timeline than the 2029 target Microsoft is now publicly promising, but it's also built on a hardware approach that a much wider slice of the physics community currently considers more thoroughly proven and independently verified, even though IBM's own superconducting qubits still require far more error correction overhead than Microsoft's topological design theoretically would, if it actually works the way Microsoft says it does. That difference in error correction overhead is really the entire crux of why Microsoft is willing to move slower on proof, but faster on its public timeline. IBM's superconducting qubits and the trapped ion qubits used by companies like IonQ and Quantinuum are both extremely well established and independently verified technologies at this point, with thousands of published peer-reviewed papers behind them going back decades. But precisely because those qubits are more exposed to environmental noise, both approaches typically need to combine somewhere between hundreds and thousands of individual physical qubits together just to create a single reliable logical qubit that can actually be trusted for real calculations, an enormous overhead that makes reaching a truly large-scale, useful quantum computer extremely hardware-intensive. Microsoft's entire bet with the topological approach is that if the underlying physics genuinely works the way the company claims, the error protection would essentially be built directly into the hardware itself from the start, meaning far fewer physical qubits would be needed to create each reliable logical qubit, potentially letting Microsoft leapfrog straight to a smaller, more efficient large-scale machine instead of needing the sheer brute force qubit counts that IBM, Google, and the trapped ion companies currently require. That's an enormous potential advantage if it holds up. It's also exactly why the stakes around proving Majorana 2 actually works are so much higher than they'd be for a more incremental hardware update. Microsoft isn't just claiming a better chip, it's claiming a fundamentally different, more efficient path to the same finish line. And that's precisely the kind of claim that draws the most intense scrutiny from everyone else racing toward that same goal using more conventional methods. Zoom out even further, and you can see why investors and governments alike are pouring so much money into this space right now, regardless of which specific approach ends up on top. According to a recent Quantum Technology Monitor report from McKinsey, global funding for quantum computing reached $12.6 billion in 2025 alone, a 6.3 times increase compared to the year before. Revenue generated by quantum computing companies worldwide has already crossed $1 billion, and McKinsey projects that figure could climb to somewhere between $3.2 and $4.4 billion by 2028, representing an annual growth rate of roughly 47% if that trajectory holds. Money is clearly flowing into this entire sector at a pace that assumes at least some of these competing bets, whether it's Microsoft's topological qubits, IBM's superconducting circuits, or the trapped ion approach used by companies like IonQ and Quantinuum, are going to pay off in a meaningful way over the next several years. Nobody, including the physicists arguing about Majorana 2 right now, actually knows for certain which specific approach gets there first. If this kind of story, one that actually shows you both the impressive claim and the real scientific pushback behind it, is what you come to this channel for, that's exactly the kind of coverage we're going to keep doing. Subscribe if you want more of it, because most coverage of announcements like this one either uncritically repeats the company's own press release word for word, or swings the other way and dismisses the entire thing as nonsense without giving credit to the parts that are genuinely impressive engineering. It's worth remembering, too, that being skeptical of a specific claim isn't the same thing as being cynical about the entire field. Even Microsoft's harshest critics in this story, physicists like Legg and Frolov, aren't arguing that topological quantum computing is impossible or that Microsoft's engineers are acting in bad faith. Their objection is narrower and more precise than that. They're saying the specific evidence published so far doesn't yet meet the bar required to confirm the specific claim being made. That's actually a really healthy way for science to work, even when it's playing out in public through press releases and primetime developer conferences, instead of quietly inside academic journals, the way this kind of debate traditionally used to happen. The fact that Microsoft is willing to put a hard, specific, testable deadline, a working commercial quantum computer by 2029, on the table at all means this disagreement won't stay unresolved forever. Either the company delivers a machine that independent researchers can test and verify for themselves, or it doesn't. And at that point, the current argument between Microsoft's confidence and outside physicists' caution gets settled by results instead of press briefings. Drop a comment and tell me honestly, after hearing both sides laid out like this, do you lean toward believing Microsoft's topological approach is going to be the one that eventually wins this race? Or are you more convinced by physicists like Legg and Frolov, who are still waiting for proof that actually holds up under full scrutiny? I want to know where this audience genuinely lands on this one, because it's a real, live debate happening inside the scientific community right now, not a settled question with one obvious right answer. We're going to keep tracking this story closely, because Microsoft has effectively made a public bet with a hard deadline attached to it now, a scalable, Commercially useful quantum computer by 2029, and between now and then, we're going to see this exact same argument play out again and again as more data, more preprints, and hopefully eventually some real peer-reviewed confirmation starts to come in. Keep an eye on whether Microsoft's next Majorana paper finally includes those missing X measurements the critics keep asking for. That single detail alone will tell you more about where this story is actually heading than any press release ever could. I'll see you in the next one.